Okay, welcome to another live streaming on the Essential Physics. Uh, Today, I have to say, I don't have much prepared. I am busy figuring out the next month that is going to be full of travel. So I haven't had time to think of what we're going to do today. I have for next week, something prepared. There was a student that came up to me with a bunch of questions on sort of the math related to quantum mechanics. And I thought we would actually go through his question together in the live, which would be, I think, of general interest. A lot of the questions were actually very interesting and allows me to go through some of the details of things that I figured out many years ago, and uh, I don't think about anymore. But most people would be interested in that type of stuff. So I do not have anything planned. I don't know if Tobias, if you have a question or things that you would like to talk about, discuss, that would be great.
Can you hear me?
Yes, I can hear you.
Okay. Um, okay. I have something which is so small and simple. I don't think it's for the live stream. But uh the thing we talked about last time, uh how can we put a measure no, not how can we put a measure on an ensemble space? It's more like can we define it in terms of the extreme points or something like this, right?
Yes, the
I think
Choquet
I'm
theory.
confused about what kind of measures are floating around here because one is you want to measure how many states there are.
Mhm.
I guess a state is an ensemble or something like that.
So states in that case would be the states over which you're creating the ensembles.
Okay.
So the
Which
microstates or the pure states.
it would be also the extreme points.
Those would be, no, no, that's what I thought at the beginning, and it's unfortunately it's not that simple. So
Okay.
maybe we can talk about that. It's really confusing. It took me like 6 months before figuring it out. So let me
Okay.
do
Then
this.
what confuses me is that also um each ensemble should somehow become a probability measure
Yes.
over like any possible kind of sample space for each observable so that the ensemble itself should define some kind of measure on different spaces again. I'm not sure how that is like related to the measure that we are kind of trying to find. Does it
Yeah.
make sense?
Yeah.
And we
Yeah.
want
Yeah.
to define, do we do we want to put a measure on ensemble space to measure its size in some sense?
Yes, we also want to do that.
Okay, and I don't see, I think I confuse all these things somehow.
Yes, because I also confused them for a long time. So let's see if I can clear up some confusion. Let me try to get the tablet working. So we go to this, and then I can create, how do I create a new thing like this? Okay, so this is gonna be that, and then I should share the screen from here. Share screen, start now, and then I go here and I do this, and now I should be sharing a screen and you should be able to see me right. Yes.
Yeah, I can see the tablet and the white screen, yeah.
Very good. Okay, so many confusing things. Let's start with the intuition that we get from sort of discrete classical probability, which is kind of the problem, because then you think that that intuition is going to extend to all other cases, but it does not quite. So let's start with that. So you have, let's say, 3 points, A, B, and C, and then you have the space of all possible probability distribution on that point, which is the simplex, which is a triangle. So any point here can be understood as essentially a mixture of three things, right? So this point here is PAA plus PBB plus PCC. Okay? Now, these three numbers, right, can also be understood as a measure on let's say, the power set of A, B, and C.
Yeah.
Okay, so if you say, I want to know the measure of A and B, well, that's going to be PA plus PB, and so on. Okay, so that's how it works. And so this measure is on the extreme points because A, B, C are extreme points. And every point in the probability space, right, in the space of probability spaces, in a space of probability measures, can be understood as a measure on the extreme points. Okay?
Yeah.
You can sort of do the same thing in the continuum, in the classical continuum. So suppose that you have, let's say we have R, and let's call this X as our variable. And so you typically represent this like this, and you would have a bunch of probability that you could put there, right? In terms of sort of the space of probabilities, this will also form a convex set, because if you take two probability distribution and you make the convex combination, you're going to get another probability distribution. So each of these, you can think it as a row of, let's call it row 1 of X. This is also a row 2 of X. And this point in the middle is going to be row 1 plus row 2. Okay, so this is the space of all continuous probability that you can put there. And you can think of the extreme points of this space as the Dirac distributions, right? So x minus x a, and this would be this point here would be the delta of x minus xb, and so on. Okay? So
Yeah,
yeah.
it's only formal, right? This is
Hmm?
this is only formally speaking. That's what physicists do, right? But I don't like, I don't know. Is this like well defined? Because
No,
like,
this actually turns out to be well defined in the space of random measure with the correct topology. So that this actually works.
okay, okay. Conceptually, I understand extreme points in this case, yeah.
Okay, so Mark, you said the graphic is a bit overloaded. In what sense?
Yeah, it took me a bit, like I basically blinked and then it was done, but because I didn't follow the progress of you doing it, it was a bit hard to follow it. But
Okay,
yes.
I'll redo it slowly. Okay, so at the beginning, we have inside here, the other point is that I don't really have a cursor. So once I draw, I can't like point to things.
Hmm.
And this
Yeah,
is another problem. The only thing that I can do is like keep drawing on it, and then it becomes even more of a mess. Like I don't know. I, it's gonna be like if I had the correct tools, it would be
hmm,
like I have this. I don't know how
yeah.
much I should invest
I
to set
think
something up.
part of the issue is just you added a lot of lines which are just arrows. I think if you had used color, it would have been a bit clearer.
Okay, so the arrows are basically my the substitution to my cursor. So
Yeah.
the arrow can essentially go
Oh
away.
no, not that part. I meant just the circle with the delta distribution stuff. Those arrows were fine.
Ah, okay, these ones. Yeah, well, because I have the point here that I'm trying to connect to I'm
Yeah,
trying to
yeah,
get
yeah.
labels. So, yeah. Okay, I'll try to see if using different colors makes a little bit of a difference. But the point would be that in both the cases, both in this case here and in this case here, we have essentially a space of probability distributions, and we can always sum two probability distributions by doing P1 row 1 plus P2 row 2, right? Making a convex combination, you always get a probability distribution. And in the classical case, you can always think as any point inside this probability space as being a measure on the extreme point. That's basically how it works. The thing that becomes a little bit tricky for us is that these distribution, the delta Dirac, the extreme points, are not actually ensembles because a delta Dirac, we cannot prepare something that it's at the distance always perfectly prepared in the same place exactly every time. We can't do that. And one of the way to see that we can't do it is that a delta Dirac on a continuum would have an entropy that is minus infinity. And that would mean that in our ensemble space, we wouldn't have the entropy, and we wouldn't be able to define the geometry. In fact, what happens, if you remember when we had Ariel come here and talk about his work on entropic dynamics and so on, he was saying how in quantum mechanics you both have a symplectic structure and a Riemannian structure that basically defines the distances and the angle in the space of probability. But then when you take the limit to quantum mechanics, the symplectic structure remains, but the Riemannian one becomes degenerate. And that's exactly what happens, is that the fact that you have this entropy that goes to minus infinity essentially destroy the notion of distance that the entropy is going to allow you. So while technically we do, in classical mechanics, we can think of each probability distribution as each ensemble as a probability distribution on extreme points. The problem is that those extreme points are not ensemble themselves. In the discrete case, they are, right? A, B, and C are proper ensembles. They're things that we can prepare. In the continuum, they are not. So this is the first bit where things start going awry, where the intuition that you have in the discrete does not quite match the intuition that you have in the continuum. Okay?
Okay, I think I also understand now where my confusion came from. So the delta Dirac is easily defined as it assigns to any set of the sigma algebra that contains XA, for example. It assigns it measure 1, right? And that's it. So that's no problem. But the thing is, the singleton XA is not in my sigma algebra, right?
No, the sigma XA is in the sigma algebra.
Yes? Okay.
Yes. The issue is that it is this is where we have two measures, right? We're going to have well, maybe this P is a problem, but so we have two measures, right? We're going to have a probability measure, let's call this mu, and this is something that goes from the simple algebra from to 0 to 1, to the interval 0 to 1. And then we have the Lebesgue measure, let's call it this have a symbol that I don't remember how to pronounce. And this goes to all of R, actually R plus.
The new.
Let's write it like this. 0 to infinity and like this. So this is mu. What is this that I forget?
A new, I think.
Mu, but isn't this mu?
No, a new.
New. Okay, right. Mu and new. Okay, perfect. So that's gonna be so easy to take one from the other. But again, And so let's say this is the probability measure, and this is the big measure, this is the count of states. Okay, so what it can't happen that it does not make sense is if we have a set U that has a count of state that is zero, right? It's basically you're saying, well, we can't really prepare states in this in this set anyway in a reliable way. Then it would not make sense to have a mu of U that were different than zero. So we want that wherever in a set we say there aren't really any states there, we also want to say that the probability of getting that event is going to be zero.
Okay. Does it also mean I cannot take a like a derivative, like Rado-Nikodym to get like a
Right.
density?
So
Okay.
in mathematically, this is called absolute continuity. And it's exactly the requirement that if this is true, then we can define a Rado-Nikodym derivative that is going to be d mu over d nu.
And this is the probability density function that we are used to, right?
Yes, so this is the probability density.
Okay.
Okay, so this is where both the physics and the math are in vehement agreement, right? This case over here, like not having absolute continuity would really not make sense in the physical sense, right? And then that's also what allows us to talk about probability density, which is the object that we can think in physics. Like in physics, when we typically think of probability distribution, we draw things like these. Like we draw probability densities, even though they're not the prime object in probability. In probability, the prime objects are the measures. The reason that we can write intuitively always our probability as distributions like this is because implicitly we are assuming absolute continuity, which means we can give probability greater than zero to sets that have measure zero that have essentially no states.
Is the mu basically the same as nu divided by the partition function or something like that?
Say it again.
Like, so I'm thinking thermodynamics here. Maybe that makes no sense, but you have the partition function, which counts like the total number of states, right? So then the nu divided by the division partition function would be the mu, right?
The
So
partition function, if I understand what you're saying, is the probability density.
right.
No,
Wait,
I see what you're saying. So okay, I think I see what you're talking about. So when you create a row, you typically have I minus, what is it? I forget what I put in the exponent.
Beta H,
Say again?
beta for inverse temperature.
Right, there you go.
yeah,
Yeah.
And then
yeah,
you
exactly.
have I don't remember even what symbols you use here.
Well, then
But
it take 1 over Z or
yeah,
something to normalize the thing.
something like that to normalize the thing. No, it's not that. It's not that.
Okay. Yeah, that set was my partition function. That's what I meant.
Yeah. So I'm thinking whether there is any relationship or not.
I mean, that's also about counting states and then dividing by C to get a probability density, right?
It is. So the thing might be related, but the issue is that this partition function only makes sense when we are talking about this whole object.
Hmm.
And the mu here would be the Louisville measure, would be, the symplectic form to the, actually, we should write it like this, to whatever n number of degrees of freedom you have,
Hmm.
right? So it would be, okay, let's be precise somewhat. is going to be the integral of u in dx to the n of c. What is it? 3s, like this. So there might be a relationship. No, because at the end of the case, so let me think. There has to be a relationship because at the end of the day, the partition function will have units of counts of states, right? The units of z will have to be the same units of mu. But again, it's probably because this you can think of, yeah, so this is going to be the correct relationship. So this is a probability density. So it's going to be your d mu over d nu. And that's basically how it works, right? So
Right, that makes sense.
if you would somehow renormalize this side, you might be able to write it explicitly as the part that it's 1 over mu and the part that comes from the probability. But I don't know. Yeah, I wouldn't know whether it would make sense to do that. In principle, you could do it if you took, yeah, so if you took a, a, a probability measure that were uniform, and you did mu of u over d mu u over d nu, right? That would tell you what would be that inverse of the count of states, and then you could say, okay, there's going to be something that I can multiply the two probability densities with, and that would be the ratio. So in principle, you can sort of cook up something to relate them, but they're not the same thing. Okay.
Okay.
Interesting. Okay, so let's remove this so that we have the less stuff that it's confusing. Okay, so we have what we have. We have probability density, we have absolute continuity, and so the issue is that we do have the points, and we can kind of think of the points as being the extreme points. And then comes quantum mechanics and makes this even less tenable because what's going to happen is a multiple decomposition, right? So you are going to have, let's do the sort of the finite dimensional case of quantum mechanics first. You are going to have your block ball. And you're going to have each point in the block ball, which is going to be a density matrix. And the density matrix can be, each density matrix can be understood as a convex combination of extreme points, and which would be pure states. So your psi and phi. And there is a privileged decomposition that is the one with in terms of orthogonal states. So let's call it plus and minus. Right? And so this row, you should be able to write it as P plus rho plus, P plus plus, plus P minus minus. Okay. And so you have a probability measure in terms of the extreme points, but it's not unique because you can also write P phi plus P psi. Okay?
Yeah.
Okay. Now, when so the space of points, then if you can think it as much larger than the ones in classical mechanics, because even in the finite dimensional case, we have infinitely many possible extreme points over which we can take this decomposition. Now, what
the phi and psi here are not necessarily on the opposite sides, or are they opposites? Like
They're not necessarily opposite. So
okay,
the
yeah,
phi
but
and psi are not opposite, the plus and minus are.
yeah.
And I also, right now, I wrote them in terms of, the composition of two, but clearly you can do it in terms of countably many points. And
Mhm.
also, you can also do it in a continuum. So, for example, if you take, again, the block ball and consider the center point is going to be, the center point, let's call it O. It's going to be some sort of integral over the full space, let's call it omega, of a uniform distribution, which is going to be over 4 pi, right? 4 pi is the area of the surface of the sphere over all the points, right? So you can imagine those, let's call this D. So if you have a measure that it's a uniform measure over the whole surface, that corresponds to the center point. So not only you have multiple decomposition in terms of discrete probability, but you also have infinitely many composition in terms of continuum and also like one-dimensional continuum. You can say you can take the uniform distribution over an equator, like a maximum circle, and that also is going to be the middle point, the center, the center of the sphere. So it's it's really degenerate. The composition is really, really degenerate. And now when you try to do it in terms uh, of your wave function, now let's think that we have a wave function that it's in position, right? Then of course you know that I also have another representation that could be in terms of momentum, but you can think of making some type of mixtures in terms of things that are not orthogonal in the same way that we did it with the phi and psi here, right? And so you could take some of these points in position, some momentum, some in energy, and then you put a measure on all of this, and you're happy. The other complication is that the fact that the delta Diracs are not states is even more important in quantum mechanics because those probability measures really do not correspond to elements of the Hilbert space, right? So if you have a Dirac measure in position, that element is not part of the Hilbert space, and really it's while in classical mechanism we can sort of pretend that we can put those extreme points in the space of measure. In quantum mechanics, we can't even do that. And even if we were able to do that, we would have infinitely many ways to do it. And the space really becomes completely horrible. Like there is no sense that you can talk about these things properly. So you can only talk about them properly when you've picked a particular set of operators that commute and they form some type of maximal basis and so on. So that you can do, right? But it's not going to work in general. So this whole idea of thinking of the ensemble as being mixtures of the extreme points kind of does not work. The correct way to think about it is that I have a bunch of observables, let's say O1, O2, O3, right? And these will map my ensemble space to a set of three numbers, O1, O2, O3, right? Now, these are the points on which I want to create my probability distributions. And so these are not the points as extreme points of the ensemble space, but they are the points of the output of our observable. So the thing that I would really be able to set up, which I don't have yet, there would be our ensemble space, right? Then you have a map, which is our observable, that maps to the real numbers. And the probability distribution that you get are not on the ensemble space, but they are on the possible values of the observable. And this would work even in classical mechanics, where you have, you might have a discrete set of points, they map to a real number, and then you find that the extreme points are only going to be the particular value of that real line. Same thing with the ensemble phase of classical mechanics. You would have position and momentum, then they map out to the perfect value of position and momentum, and then you create a distribution on that. I think that's the structure that is going to generalize.
So your list of observables is like your complete set of observables. And for a specific choice, I could then define probability distributions over the, I guess, all the possible eigenvalues. And that defines then in turn my state. Is that what you're saying?
Yes.
Okay.
So there is a move that it's done over and over in when people work with a topological vector space. That kind of works like this. You start with, let's say, a compact subset of the real line that goes from 0 to 1, let's say. Okay? And then you have all the continuous functions, right? That, well, they need to be infinity. Continuous function that act on that interval, right? So these things act on this. And these form a vector space. And in fact, I think they also form a Banach space because you can put a norm on this thing and so on. Okay? And so, if this is your x, then this would be an f of x. And then you say, okay, now I take the linear functional of these things. And these are typically written with a star. Right? It's the linear functional. These are also linear, continuous and affine. Otherwise, it doesn't work. Otherwise, it doesn't give you a vector space. No, this not need to be affine, sorry. These are going to be affine. Okay, so the idea then this are, let's say, function, let's call them mu, of an f. Right? You give it an f, and it gives you a number. Also, this gives you a number. What happens, oops, is that now these things are going to be the set of measures on the interval 0 to 1. And the idea is that you can understand a measure as acting on a function by doing the integral of the function with respect to the measure. Physically, these are kind of like your microstate. These are the observables. And these are your ensembles.
Yeah, that makes sense.
And these also turn out to be, when you come from this side, the extreme points. Right, because they are the Dirac measure, the things that you can basically just give it the x, right? So this construction is the thing that we are trying to generalize. Not this construction. This type of ideas are the things that we're playing around to find a structure that generalizes. Let's put it like that.
That makes sense. And I guess uh, our starting point are the ensembles,
Right.
then there should be some observables, just some maps on the real numbers. And we want to find the microstates again.
Exactly. We
Yeah,
want to
okay.
do exactly in the opposite direction.
Yeah, okay.
One way that this may play out, I still don't know, is that at the end of the day, we have an ensemble space, right? And then we are going to have the output of our observable. And you can think of this as the space of ensembles on the observables. And so we are going to have a map from our space of observable of ensembles that could be anything, and we map into the space of probability measures that are the output of a measurement device. This would give us a sort of a more precise way to talk about measurements, because at this point the measurement is the ensemble that comes out of the device. It's not a single take, but it's the full distribution. So for us, measuring would be reconstruct the full distribution of the outcome of a measurement, which is technically what we really talk about in physics when we say we measure measurement. When we made a measurement in physics and you look at the paper, you find plots that looks like this. I have my energy and I have a distribution over the energy, right? These are the measurements. It's not that, oh, I measured the energy 3. No, you measure the distribution, and then you're going to say, okay, this was the average and this is my standard deviation. And so you're going to write those two numbers. But really what you're measuring is the distribution.
Or at least a
Okay.
sample of that.
Yeah.
Yes, yes. A sample of that, yes. And when you fit, though, you're going to try to fit the full distribution because you have an idea of what it should have been, and that's what you do.
With the outputs, so the ensemble after measuring,
Mhm.
is this now in some sense a classical one?
Exactly. So I think so. But so in quantum mechanics, when we say, oh, the measurements are classical, I think that's what we mean. That this ensemble here, the output is classical. And yeah, so I don't have a good sense of how these maps should look like because again, I don't like we're barely building up the space of this, and this, both of these are gonna be ensemble spaces. And so what we really need to understand is what are valid maps between ensemble spaces. This is not going to be like a morphism in the standard sense because the entropy is not going to be preserved. There's something fun is going to happen to the entropy when we do this because the entropy that we define on the output is going to be the entropy related to only that particular variable. And so the map is going to be, I don't know what happens to the entropy. What happens to the convex structure, that needs to be preserved because if we make a mixture of the inputs, then the output must be a mixture as well. So there is still a lot of, how can I say, conceptual work that needs to be done there because I don't know exactly how it should look like. But in principle, it should be a map from ensemble spaces to ensemble spaces. And yes, so the output should be a classical ensemble space that it's either going to be a continuous variable or a discrete variable. But for our purpose, you just have R, and then you're going to have different topologies on R depending on the spectra of the output. That's how it's going to work.
Yeah, I'm just confused because I would kind of expect if I want to do two measurements in a row, I would like draw a second arrow and keep going. But
Right, and for that, I think that's where projection would come into. So, what you could do is to say you first have epsilon, right? And then you map to the epsilon one, which is after your first measurement, and you are going to then map out to, let's say, epsilon A. Let's say that A is the measurement. I don't know how, I don't have good symbols. So, so that map that first I had like this. So this is the output of the measurement, and this is the updated state, right? Uh, this part here, I think, is going to be the projection. So if I think about it in quantum terms, I start with my block ball. Then I project to the vertical axis because I'm measuring spin up. And then I map out as a probability distribution on 1 and 0. So it's a S0 plus P, well, let's call it 0 and plus 1. And then if you do a second one, then you're mapping this to, let's say, the horizontal axis. And then, of course, you collapse everything in the middle point. And then you're going to have P left, S left plus P right, S right. Right? So that you would be mapping to another thing, and then this is going to be your map out.
yeah, okay, that makes sense.
So I
From the
don't
epsilon
think.
one.
Say again, Mark?
From the epsilon one, that's the right area? Okay.
Yeah. And in classical mechanics, the projection is always the identity.
Yeah.
Because all the observables are compatible. So nothing to do.
Okay.
Yeah. I'm slightly confused about the graph in terms of the indices. So what's the original epsilon here? The one without
So,
index.
so this is the state before all measurement.
Okay. So you're saying the measurement changes the state as it does in quantum mechanics.
Yeah.
Okay.
Because it needs to bring you to a state where you can actually talk about a probability distribution in over that observable. So, if I have a block ball and I'm measuring spin up, right? The only possible outputs of the measurement, they are this line here. This.
Yeah, of course.
And
Between the
so
two states.
whatever other state that I am, I need to go in one of those.
Yeah, that's the projection, I guess.
And that's the projection. And it's a projection in the space of ensemble. And I hope to show that that's a thermodynamic equilibration process. That it's a process that increases the entropy given some constraint.
Is that like the top line here, the actual state, and the bottom line, the outputs are what the measurement device says or something?
Exactly. That's what the measurement device says. Yes.
Yeah. So that's the difference. What are the two terms again? Ontological and the other one.
Yes. So measurement output.
Okay. Now it
Now,
makes sense.
there are cases where there is no update, where the measurement device destroys the original state.
Mhm.
And then it would really be a map that goes from state to measurement, and there's nothing in between.
I mean, there shouldn't be an update if you just remeasure in the same basis again, right?
And no, like you have absorbed a photon. The photon is not there
Yeah,
anymore.
okay. Hmm.
Right? You can repeat the measurement, but then you have re-prepared the same ensemble at the beginning.
Yeah.
In fact, I mean, in the experimental side, the people that do experiments, they're going to tell you that most measurements are distracted. So this idea that you can update the state happens like in fewer cases than I mean, if you're doing optics, if you're doing, dealing with photons, all measurements are distracted, for example.
Yeah. I mean, they kind of have to be.
Yeah.
We
Okay, so is this clear, Tobias?
So, yeah, so the measures that we are talking about are um in classical physics, we don't need to worry about which observables to choose,
Hmm.
but in general, you would need to choose some observables, and then their let's say output space, like or possible measurements, their sample space is where we put a measure on, and we want to identify ensembles with measures on sample spaces for some observables. I understand that. I'm not sure
Yeah,
if I
so it's kind of what you said, on Tuesday when we were meeting in person. The sigma algebra that we have for the measurement, they come from the possible values of the measurement. So
yes.
you can think that you have the space of ensemble, right? Epsilon. And then when we map with an observable, we know that there are some possible points in R, and we know that there is a set of measures that is an ensemble space. Right? So you have more structure when you're outputting. And so here you have a sigma algebra on R, right? And of
Yeah.
course, you're going to have another sigma algebra on the space of measures, but these measures are going to be in terms of the sigma algebra on R.
Wait, why do I need another sigma algebra on the measures?
Because the measures form a topological space.
So there is one. Why is it interesting?
Because it's the one that maps directly to the sigma algebra here,
Sigma algebra on
the,
the
the
ensembles. We
ensemble
ever
space.
have like probability distributions over ensembles?
So let's think it like this. Instead of thinking of simple algebra, think about the topology,
Yes, that makes sense.
okay? And this map has to be continuous,
Yes.
right? So the topology is going to be important in that.
Yes, absolutely.
Right? And because then you're going to have things about absolute continuity and so on, you're going to also be able to hopefully reconstruct the topologies. There's going to be a link between this space and the topology sigma algebra that we have here.
Okay, yeah.
So if, for example, we're an ensemble space that it's secretly a simplex, right? Then when we map this simplex here, we're going to have three possible values, right? And the space of probability measures here is going to be the space of probability values on 3 Dirac measures, right? That's going to be a discrete space.
So in that sense, uh, you're saying the geometry, no, the topology of the ensemble space would tell me something about the topology of my sample space, or
Yes.
any observable actually.
Yes.
Okay, so yeah, they're obviously somehow related.
Right. And so this is the part that I still need to understand. How can I go from one to the other? And we know that we do it in quantum mechanics, right? Because you take the position operator, and then the spectrum is continuous. You have all the possible value of R. And you take the Hamiltonian for harmonic oscillator. I don't remember the constants. Let's just call it A and B for whatever reason. And you are going to have that this is actually discrete. You have discrete values.
Yeah.
Right. So there is a relationship between the operator that we picked, the ensemble space, and the topology of the spectra of the operator. That's the part that I still need to figure out how to take out. And yesterday night I had a dream where I think some things might work. So that's how it works. My head. It's when I sleep, I dream about subspaces and stuff like that.
Okay. So these measures are the ones we talked about that are related to Choquet theory in some sense. Like they have similar questions,
Right. So
right?
now, in all this business, Choquet theory really only works when you have a locally convex topological vector space. You have compact, and so this is E, a compact, a convex subset K. And then you can say that every point inside is a measure on the extreme points.
So this space is, well, in our case, would be the ensemble space.
K would be the ensemble space. And the extreme points, I hope, would be some type of closure that you do on the ensemble space. Because if we are on a continuum, the Dirac measure are not inside our ensemble space. And so the hope that there is a way to close that such that you get a compact closure, so something that if you do the closure, you find also that the thing is compact, and then you're happy, and then you can use Choquet theorem. If that worked out, would be a good connection.
Okay, so really we want the same thing. We want to every point in our ensemble space to be expressible as a measure over the extreme points, not necessarily unique.
Not quite. So the construction
No.
that I have in mind is this. You take an observable. Somehow from your observable, you find a subset C of the ensemble space, that it's a simplex, and it's the context of the observable. So to make it concrete, let's imagine the space of all our mixed states, right? You take an observable O. There are going to be mixed states such that rho of O minus equals O of rho. So it's a set of observable that of density matrices that commute with the observable.
Yeah.
Okay. And the idea, right, if the observable is X, right, what are going to be the mixed state that commute with X? Are going to be things that we can write as rho of X.
Wait, what is X now? Just the
The position,
position, for example. Yeah.
right? So I'm on a
Yeah.
position basis, then uh, the density matrices that commute with the position operators are things that I can express in a position basis.
Yeah, it's diagonal in this basis, and then
Exactly.
yeah.
And this is essentially a probability distribution in X,
Yeah.
right? So this simplex should be that. So we need a procedure that I give you an observable and you find essentially, recall here, these type of things, like the things that we project to get the possible spaces of outputs, whatever you want to call it, for that observable.
Yeah. Okay.
Then this, hopefully, we do some kind of closure in E, in the vector space, and we get that K. And then we say, okay, K, all our C's are measures on the extreme points of K.
Okay.
Right? Something along those lines, because it has to happen like that. We have an observable, then you think, okay, what are all the possible ensemble within the space that actually corresponds to probability distribution on that observables? You take that, then you find hopefully that the extreme points of those things are the Dirac distribution, the Dirac measures, and then everything is going to be a measure in terms of that.
Okay.
This is the plan, right? For now, after all the other plans that I tried failed, and hopefully this is successful. I don't know. Maybe not. Who knows? It's research.
Okay. And then so what we need to provide is some choice of observable, and then it should be one-to-one, right? Once you have a complete set of observables, at least.
Once I have a complete set of observable, I will get a specific simplex. Now, it's not going to be one-to-one
No,
because you can find other observables that it's
sure, you need
still
much
going to give you the
more.
same context, but
Yeah. I forgot. Okay. But okay. Yeah.
so that's what I'm going for right now. It seems that it's now repeating it makes sense because I seems well thought out while I'm saying it out loud. So that's good. It's not just well thought out when I think about it,
It
but
it wasn't just a dream, yeah.
exactly, it wasn't just a dream. And now the question is, what is the procedure here, right? That's the part that I still don't know, and that needs to be figured out. I think
So
definitely.
what the mathematicians already figured out is that if it's locally convex topological vector space,
Yeah,
then you take a compact convex subset of it,
yeah,
then you can define every point in this K as a measure over the extreme points of K.
yes,
Okay, that's what they already figured out.
yeah.
And we want to mimic that under slightly different circumstances.
Right. We want to reuse that result to,
Yeah, okay.
yeah, because if I can reuse stuff, that's certainly good. And it might be that we are going to reuse it directly, or it might even be that we look at their proof and then in a sense, cannibalize some of the idea and just to reuse them. Because like it would be more elegant to me if I didn't have to make that closure, but if I just took the points to be the possible set of outputs of the observable. Like the points are those, and they're not really. I'm not trying to complete the ensemble space by putting by creating these states that don't exist. But I just say, oh, every ensemble is a measure on the possible values that are identified by the observable. I think that would be more elegant.
Okay, yeah, that would make sense. By the way, when they so you take the extreme points and then you think about measures on that thing. So you would also need, so you have a set already. And I guess a topology. Do you get then also already a sigma algebra for your,
Yeah, the topology you get from the vector space.
sure. And then the topology, how was it related? So the topology is bigger than a sigma algebra, right? No, was it the other way around?
No, sigma algebra is bigger in the sense that it has more set.
Yeah, yeah. But is it determined? Oh,
Yes.
yeah.
Yeah.
So I get that already, and then I just need to assign values to that. Okay, fine.
Mhm. Yeah. So one other thing also is that this set of extreme points is also horrible to characterize. So, like, I talked to a couple of mathematicians that basically told me that. So that would be another reason that if we were able to work directly with the set of points that are the outputs of the measurement, and then you say, okay, yes, we can. We're basically taking an ensemble and then taking the points as the possible values, and for every set, we give a number given that we have picked a particular ensemble, right? That we really construct the measure without having to worry about how can I say, the structure of the um, uh, uh, of that compact set, so on, right? If we were able to just do it like that, it would be a lot easier. We have the space of possible outputs of our measurement, we have an ensemble, and we just construct directly the measure. Like that would be the that's what I was trying to do actually in the other version that didn't turn out to work.
By the way, so the K is basically the spectrum.
No.
No, the extreme points of K are the spectrum. Does that make sense?
Uh, uh,
Of an operator in quantum mechanics?
I think so.
Yeah.
So the issue
That's
is that I don't know. So I don't really have a good handle right now of what these compact sets are. Because in infinite dimensional spaces, all these things become horribly complicated, and it's very difficult to get a good intuition. So I know that it definitely works for the simple discrete case. I know that it works for the continuum. I don't know for these hybrids. So something like the hydrogen atom, for example, it has a part that is continuous and a part that is discrete. No idea if that works with Choquet theory or not.
yeah, the extreme points are kind of funny. Some are discrete,
Yeah,
some are not.
yeah.
Yeah.
So I
I was
assume they would still
wondering
go
if
ahead.
the spectrum of a bounded operator is always compact, for example.
Yeah.
That would be nice.
So those all the spectral theory is basically the thing that we have to reproduce to get this thing going. So it's quite an undertaking, but yeah.
Yeah, sounds like it.
And then I was talking yesterday with and I'm a mathematician because we're also like there are issues of um uh, groups that we also have to figure out and so on. And he was telling me that so in general, basically, whenever you have infinite dimensional vector spaces, there doesn't seem to be, let's say, standard techniques that work for all problems. It's like you have these particular problems, you can use this technique. So you have this other problem, you use this technique, right? So it's gonna be, this is where I guess I was a bit naive, maybe like a couple
Mm.
of years ago, that I thought there would be something, yeah, okay, there is some hodgy-podgy thing, but at least we can take it and sort of morph it into the thing that we have. Uh, it's like we have to go through a lot of literature to understand how these pieces work. And he gave me a couple of books that I'll have to skim through and see what they do.
Yeah,
Okay, sorry, Mark, go ahead.
um that might actually be related to how you can't really construct the proof for every vector base as a basis. Like you can certainly use the axiom of choice and say, yep, it has one. But then to actually use it, you'd have to construct it, and then you have these kinds of issues where in infinite space you need different kinds of constructions rather than one recipe that works for all.
Yeah. And it's funny because to me, I think this is the whole problem that so we need to use infinity in physics because at the end of the day, like even the notion of ensembles already contains infinity inside. So you can't just say, oh, I don't have infinity, everything finite, because the the idea that you can keep reproducing and you can retest one more time already has a bundled idea of infinity. But it has to be a very tame infinity because it's just the sort of the idea that, okay, I can repeat this, so I'm never going to actually have an actual infinity and so on. And so there are like infinitely many infinities that you could have, and we have to
Mm.
find the one that makes sense for physical theories. And I really suspect, this is really my hunch, and we'll see if it's going to be true or not, that once we figure out how to do it, it's going to be the simplest, most tame possible way of having infinity.
Yeah, and you'll be like, why didn't I think of that sooner?
Yeah, because it's going to be some like a reasonable extension on what you do in the finite, and it's going to be the simplest thing. So so yes, we have unbounded operator, but the values are all going to be finite. Yes, we have an infinite space, but it's always made of countably many pieces that are finite, right? There's always going to be something like that. And so you're going to have multiple ways to control this thing and not let it blow up. But, you know,
Yeah.
Okay, by the way, I just looked up a spectrum is always closed. If you have a bounded operator, then it's bounded, and then you have a compact subset of, yeah, in general, a complex plane and for physical observables for the real line. So only if you have like an unbounded operator, then of course the extreme set of extreme points doesn't need to be compact then. So
right.
I'm just looking at this because I wonder if I could look at one specific example just to see what is going on, because like this makes sense conceptually, but it's kind of abstract, and I might, I don't know, learn something by looking at a concrete example.
If you could, that would be really, really helpful to me as well.
So
Because,
the issue is kind of, I would you would start from something very simple where you just pick like a finite. So I would pick quantum mechanics as an example. And then if you start with a finite dimensional space, I get the impression it will be kind of too simple and not showing off like what is happening, and then I don't know what the next example would be. Maybe
So
just to
Countable,
break up
probably.
do classical distribution or between 0 and 1.
Okay, first class.
That would be the first thing to do. So the
Okay.
discrete classical case is too simple. Like it's just a simplex. There is really no the distribution from 0 to 1 already are gonna have the issue that you have an infinite dimensional space, but of the continuum kind, so that you need to look at this. So one of the things that also was a little bit that confused the other mathematician that we were talking about, this is the space of measures, right? And it has to be compact. And that was not obvious that it was compact. And the way that we found some kind of explanation on Stack Overflow, that the idea is uh, so if you imagine to have the space of this of even in the discrete one. So let's say that you have two possible states, right? Then the space of distribution, if you imagine of having your P1 on one axis and your P2 in the other axis, I should draw. Why I'm not drawing? So if you have the two axes, right, and this is P1 and P2, the space of measure is this segment here. Okay?
Yep.
Very good. Now, if you make it with 3, you are going to have this triangle.
Yeah.
Okay?
Yeah.
So you're always in the positive quadrant, sextant, whatever it's going to be,
Yeah.
right? And so
Yeah.
when you go to infinity, you are going to be in the positive side of all the infinitely many things.
Yeah.
And
I think
that's
that
what makes it compact,
Mm-hmm.
right? Because
yeah.
it's going to be very small with respect to the whole space of all the measures.
Yeah.
And so those are the things where, this sort of helped to give a little bit of intuition. And this is still on the countable side, right? Because we have, but I'd really like to understand how it works for, again, distribution between 0 and 1.
Okay.
And also how it works on the topology, because this is the part that I sort of do not understand. When I have the space of measures uh, and I don't have the Dirac measures, is that space a this is exactly how it's difficult to. So imagine the two spaces. One with the Dirac measures, and one without. Now, clearly, this is a subspace of this, right? But is this a subspace of this, meaning that the span of this gonna include, and again, the span, we need an inner product. Is the subspace, is this a proper subspace or not? Like, I don't know if I'm even able to formulate the question correctly.
Um,
I'm trying to understand whether there are whether all the directions that you have here are already here. You just have to make the closure, but the space is the same, or you're really extending the dimensionality of the vector space when you're taking the Dirac measures. Like that, I don't understand.
Okay.
hold on. Dimensionality. In what sense? Because continuous is gonna be continuous, right? It's the same.
Exactly. Yeah. So let's put it like this. For example, this space, I would hope that it's second countable.
Mhm.
This space, I can't imagine that it's second countable.
So
Bec-
okay.
right? Because, if each Dirac measure is there, each Dirac measure is going to be its own direction orthogonal to the other. And so I don't think that thing is going to be, at least, I don't know, maybe I'm completely wrong, but it kind of, it seems to me that in this space you have an uncountable orthonormal basis. Right? Because I have
Right.
uncountably many elements that are orthogonal to each other. But maybe it's not, because maybe these are the questions that I really don't even understand. I don't even understand them in the sense that I can't even formulate the question correctly, as Mark is pointing out. Right? I don't know.
Yeah. So intuitively, I think that the right one is an open space, the left one is a closed space, right? And you get a boundary basically, where the other one doesn't have a boundary.
If that's the only difference, like you basically have the same space, just one set is closed and compact, the other one is not. That would be an answer, but I'm afraid that it's trickier than that.
Mm.
Yeah.
And again, let's see how yeah, I really don't understand enough to formulate the question, and I think that's the problem. Like if I were able to formulate, probably I would even be able to answer it.
Okay, how
Yeah.
much structure do we have on an ensemble space? Like it's just a topological convex space?
Uh, so for these purposes, when you're looking at this problem in particular, I think you can assume that it's a locally convex topological vector space. And
Okay.
then let's worry later about bridging the structure that we have to a locally convex topological vector space. So that I actually look at some stuff this week, and I'm really more and more of the idea that not only we have the embedding in a vector space, but we have going to have a continuous embedding in the vector space. It's just, I think it's just a matter of finding a nice way to prove it. I really think it's going to work. And
Okay,
so
but I
then we would have,
know the I have a convex structure, I have a topology, um, and I like we can define Dirac deltas at least like on a real line as some kind of sequence um of like normal distributions. Not okay, not Gaussians. Yeah, even Gaussians. But anyway, so it is in some sense really a limit of distributions, right? Of sequences.
yeah, but the limit does not converge inside the space.
Yes, it does not,
So the
but like,
closure comes in.
isn't that why it is kind of the closure? Just adding the limit points?
Yeah, but
Uh,
once you add the limit points, you have to also change the topology. It's not that simple.
okay.
Like it's
Okay.
not like when you have uh, let's say
Rational?
the rationals, and then you put the limit points, and you basically there is only one way to extend the topology to the reals. Like it's not at all like that.
Okay.
Like you have essentially different definitions. So each when you have these spaces of function, right? Because that's essentially what these things are. You have different type of convergence. So you can have pointwise convergence. You can have a convergence with the supremum and so on. And these convergences are literally different things. And you could have the different function spaces or extended to, measures, whatever, and still have different types of convergence. So if you keep let's see, I don't remember which one is it, but there is, in one sense, yes, let's say there is a sequence of Gaussian that tends to a delta Dirac if you use one type of convergence, but if you use another type of convergence, they just does not converge. right?
Mhm.
The sequence of points, that there is no other point that has an open set that always gets the tail of that sequence. Like that just doesn't work.
Yeah.
So just putting the points is not enough. You have to check what happens to the topology, essentially.
Yeah, that was stuff I've learned ages ago and I barely remember, but it's like a pointwise convergence and that there's like 3 or 4 different notions of convergence.
On function spaces, yeah.
Yeah. And
Like
so
you could
we,
use the L2 norm, for example, to measure how far apart two functions are, say
right.
Mhm.
1 plus 0.
You could have a norm that tells you the distance, yes. Uh,
Yeah.
Yeah.
One thing, for example, that is interesting to us is that all the topological vector space that have a norm also have a metric, but you could have a topological vector space that have a metric but does not have a norm. And from what I understood from one thing, but I have to double check 20 times, is that the existence of a metric, of a distance function, makes the space um, a locally convex topological vector space. So if you have a topological vector space that admits a distance function, then you already have a locally convex topological vector space. And if that's true, that would be a really big deal for us. But as I said, all these issues for now, I'll leave them separate from understanding this other side of things. I think we can safely say that we have a locally convex topological vector space because that's the case where you have a set of observables that fully identify an ensemble. Right? So if I have my ensemble space and then I say there exists a set of observables that the value of those observables fully identify which ensemble you have, then you're guaranteed, like from those observables, you can create semi-norms, and from the semi-norms, then you have a locally convex vector space that is also Hausdorff, by the way.
Okay, I'm still a bit confused about the different kinds of convergence because um, if you let's assume we assume we have a topology um, on my ensemble space defined.
Mhm.
Doesn't that pick this type of convergence, pointwise, or absolute convergence or whatever?
Yes, it will. But we at the beginning, we do not know which type of convergence it is.
Okay, well, what if I assume I am at the point where I have an ensemble space with a chosen topology?
Yeah.
Then wouldn't there be like one unique way to close it?
We would have to prove that.
Okay. But that's probably a thing that the mathematician could do.
Yeah, I'm sure the mathematician is going to tell you no, there is no way I can tell you in an infinite dimensional space that there is a single way to close it.
Okay. Okay.
So in our case, so the way that we go back to this, a lot of these things are done with the topology that are induced by the continuous functions. And
Yeah.
so the convergence in these settings is the convergence of either the values, the different values on the same element, or the convergence of the element on the different functions. Right? So you could imagine that you have a sequence of functions, right? And you apply these to the same element. And then you say f of x, f is the limit of the fi if all these limits converge to this for all x.
Yeah.
Or you could say that you have an f and a sequence of I, and then this xi converges to x if the limit is true for all f's. Okay?
Yeah.
And these are the typical convergence uh, uh, criteria that are, I think, associated with this weak topology and weak star topology.
Hmm.
And I don't know that it's exactly like this, but it's on this vein. And again, it's one of the things that we can say once we say that the states are fully identified by our observables, and then we're going to be able to say that, like if a sequence of observable converges to another observable, if if it's true for all states, and a sequence of states, a sequence of ensemble converges to another ensemble, if all the observables converge to that. Now, interestingly enough, the Dirac deltas, right, are gonna have some convergence on some functionals, but not others. So, and I think that's where choosing the set of observables actually picks out a convergence criteria. So if you imagine to take only the polynomials of positions, like the moment of the distributions, right? And if you have a short space, then convergence of the moments means convergence of the Schwartz function. Does that make sense?
That makes sense. It's like depending on the observable, you need to pick a different dense subset.
Yeah,
And
so let's actually write it down. So you have essentially this, you're getting the expectation of, let's say, x to the n, and it's going to be the integral of rho of x to the n in dx, right? And if rho is Schwartz, right, then this is one-to-one with all my expectations. Right? So if I converge here, I'm going to converge here as well.
Yeah.
yeah, by definition of this function space, right?
Right. Now, suppose that I add in a delta Dirac. Now, the delta Dirac will also converge, right? So if you have our normal distributions that converge to a delta Dirac, all the expectations, right? All this integral of the rho I xn and dx will converge to x0 to the n, right? If this is x minus x0. Okay?
Mhm.
But if I take the map that goes from rho I to rho of x0, right? This is also a continuous map, right? It's an affine map, it's continuing an affine map, like all the other expectation. But then it's no longer true that this thing will converge because it will go to infinity. Right? So if I only say, oh, for me, convergence is just that I need these to converge, then my sequence of Gaussian is going to converge to the delta Dirac because those values converge. But if I also require this other thing to converge, then I'm not converging.
Okay, the examples make sense, but I just I feel like I have a confusion from some other side. So because I remembered that to go from rationals to reals, all you need to do is look at all the Cauchy sequences
Yeah.
and just add them to your set.
Mhm.
And then I guess there is a natural way to include them in your topology.
Yes.
And then it's like I don't see why this breaks down. Like
Okay,
uh,
so when you have the rationals,
yeah.
right, you use an order topology, which is generated by all the sets that are like this.
Yep.
Okay? When you're making the limits, you're basically making them just in a single direction. Like you're filling in the limit that is in your order topology, right?
Okay.
You don't go, it's all one dimensional, like you're in a single dimension in your vector space.
So I couldn't do it on like Q2 to R2. Does it make sense?
I think if you are on finitely many directions, you are going to be able to do it in the same way
Still, okay.
because you can do it in one and then on the other.
I could just do like a, I don't know, Hilbert curve basically, and then you also fill it in, right? Um,
Mhm.
But
so that
also
would be,
the topology is just simply the product of the two sets, right? You have one open set in one direction, you have an open set in the other direction,
Yeah.
and the thing is still I'm gonna be an open set. Actually, the better way to think about it is that you have an open set on the y, an open set on the x, right? And the intersection is still an open set because it's a finite intersection between open sets.
Yeah.
Now you have infinitely many.
It's not finite. Okay.
uh,
Yeah. Okay.
so they like, if the issue is that you don't know that you have an open set in infinite, right? It could be closed then, or even just no point at all, or what's the, um,
Well, I'm just saying it's a lot more complicated. The
yeah.
ways that it can fail, I don't even, and this is sort of the lesson, is that I don't even think there is a single way that where the thing, how the thing can fail.
Hmm.
That's my understanding. And of course, if there's somebody that knows better than me, but we don't have many viewers today, so nobody's gonna come randomly and tell us and teach us how things.
Yeah.
Yeah, we should probably next time try to at least decide the topic beforehand so that I can put the topic in the. I was just too late in thinking about things, but we should definitely do it next time.
Did you say you have an idea for next week?
Yeah, next week, as I said, there was a student that came up with a bunch of questions
Yeah.
on sort of on the math of quantum mechanics. So. Uh, if he comes like he already like we already met like yesterday and I said yeah like I kept saying because I already told him like I think it would be better to have these questions alive and that every question that I had this is a wonderful question we should discuss it live because lots of other people are going to have the same misconception quest it's all the things that I had to clear up in my head 10 years ago
Hmm.
because nobody really like goes through these details so.
Yeah, that's great.
Yeah.
Sounds good.
Yeah.
Do you wanna like if you already know the questions, you can give it a title, but I don't know. Maybe you can even somehow publish the questions beforehand as a teaser or something.
Yeah, I think I'm gonna create some title that hopefully makes makes people oh, what is this? Yeah,
Yeah.
yeah. Not that I'm very good at doing that, but that's an art in a way. Anyway, so it's the hour and a half. Did we beat this to death, or you have other questions that you want to go through to close?
I think this is fine. I still um feel like I will try to figure out myself. Why can't I just take Koshi sets and be happy? Um so
Yeah,
but I
see.
think I can do that. Um I'm not sure if we can get to the answer now. So for me it's fine to make a cut here.
So recall also, let me like stop sharing here. Recall also all the other problems that we identified with Hilbert spaces. I mean, Hilbert spaces try to do that. They try to say, okay, for the closure, we're gonna take Cauchy sequences, and that's it. And that brings in things that we don't want.
Mhm.
But aren't this like Dirac deltas? The things.
Right, but the Cauchy sequence on the inner product does not bring Dirac delta, right? So if we wanted Dirac delta, that wouldn't even be the correct way to bring it. But we say that we don't even want those because really our space for the closure should probably be something like the Schwartz space. And and so the Cauchy sequences are not going to work either for getting the delta or for getting the Schwartz space, right? And it's again like it's the convergence criteria for the Cauchy sequences in a Hilbert space. Your a criteria is given by the inner product. So you have a distance essentially defined by your inner product, and you say that your convergence criteria is the closeness based on that distance. And if you want the Schwartz space instead, the convergence criteria is the convergence of all those semi-norms, right? All these
Yeah.
expectation of position momentum and how things are going to go to infinity. And that's one criteria. To get the delta function, then you do the dual space on the Schwartz space. And so it's the
Yeah.
space of function. And so now it's the convergence of those values of those functions. And that's another convergence criteria.
Okay.
So, you have to pick the one. So one of the things that I also worry is that in our framework, we might not even want to have a single, universal convergence criteria that works for all physical theories, right? There might be like a minimum thing that all these convergence criteria must do, but it might be that the convergence criteria that you have in a field theory is slightly different than the one that you have in a particle theory, right? That it's going to be a different a different thing. And it might be that the convergence criteria is a lot more stringent in the sense that, for example, uh, we had this idea, right, that we saw that in the Hilbert space you could have the expectation of one of an observer for the position for one observer is going to be different than the position of the other observer, and to the point that through some transformation it can map something finite to something infinite. And you might say, well, for principle of relativity, that's not what we want. And then basically you say, well, I'm going to have a group of transformations that represents the valid coordinate transformations. And then your convergence criteria is that within that group, nice things have to happen in the same way, that all the limits that are related through this group transformation, all they have to converge in some way, right? And I don't know if there are people that have already identified convergence criteria like that. Maybe that's the thing that we need. And uh, and again, I completely open.
That makes sense to me. I was just thinking I'm given a topology, my ensemble space, and that's it.
Right.
So of
So
course it has to come from somewhere, but
right, and the point was that so the way that it's set up right now, it's basically the topology is telling you, look, you are going to have a convergence criteria, and that convergence criteria is going to be mapped to the topology. Now
yeah.
the question is, what can we know about that convergence criteria? And what should we be agnostic about? So the fact that, for example, that the entropy is continuous and the fact that the mixing is also continuous, that means that the convergence criteria must play nice with the topology and must play nice with the entropy, right? So we know some of those things. And the question is whether that's enough to have a handle of what this is doing to be able to then prove other things.
Yeah.
Makes sense.
And we kind of are doing in the opposite way that a mathematician would like to do it, because typical mathematician always say, oh, why don't you take the simple case and study the simple case? And the problem is that the simple case never tells me whether the general case is going to work out. So we have to start doing the opposite. Like we know at least these things. What can we do with these things? And then when you hit a wall and say, well, with this, I really can't do anything, then that might give you idea of what other physical things you might have that actually can guarantee you stuff. So
Yeah, the simple stuff is always degenerated. Makes it difficult.
yeah, like we need like part of the feeling that you're feeling, Tobias, is that it's the uncomfortableness of not knowing exactly what you have underneath. But I think that's kind of is by the design. Then, of course, we can look at the examples. As I said, if we look at the distribution between 0 and 1, then we start getting a handle of what type of moves people do in their proofs. And that's basically what I think we have to look at, understand what is the type of techniques that people are doing to boil those things down and say, okay, the essential thing is that they're going to make a limit in this way, or they're using the convergence of the observables to get the convergence of states and vice versa. And then we sort of start getting a handle of how to structure this in a way that it's that makes sense. Okay.
Yeah, I think I'm at the point where I need to digest what we did today.
Yeah, exactly. Good.
Okay.
Well, bye for anybody that was looking to it. There's zero concurrent viewing right now. So today, well, it was
Okay.
very, very technical. But next week, we are trying to do something that it's a little bit more interesting to more people.
Yeah.
Yeah.
Bye,
great.
guys. Thank you for coming.
Bye.
Bye.